First of all, I would like to thank Elio, Thomas, and Laura for this wonderful workshop, and yeah, for giving me the opportunity of sharing today with you my work that I do in the University of Bochum in collaboration with Michael Scherer and Stefan Floschinger. So I would like to start with this picture of a night sky. And here we see many stars, but overall it's kind of dark. And this is interesting and surprising at the same time. And Olbers thought about this in the early 19th century, such as if one imagines a static universe with a lot of stars everywhere, light will come from all directions, so the universe should not be dark. But of course, that's not what we observe. And the only explanation for that is that the universe is not static. The universe is out of equilibrium. And a possible cause for this non-equilibrium is that the universe is expanding. So in this project, we focus on the early expansion of the universe. So after this fast expansion, also known as inflation, we had a reheating period where pair of particles were created. And this is a really interesting phenomena, but it's not accessible with measurements. So what the analog gravity suggests is to find analog models in order to gain information about this kind of phenomena. So normally these analog models are condensed matter systems because they are really well studied theoretically and also well controlled experimentally. So in this project, what we want to do is to simulate a tiny expanding universe in a lab. So this has been done in several works before, previous works, but mainly in cold atom systems, because they are highly tunable systems. So what it has been studied, it's the production of bosonic particles. And I also studied that in Heidelberg, in the group of Stefan Floschinger in collaboration with the group of Markus Oberthaler. So they had their two-dimensional Bose-Einstein condensate. And we simulate an expanding universe by introducing a time dependence between the interaction of the atoms, so using Fleischbach resonances, and also changing the trapping potential that contains the atoms. With this dynamical process, we managed to create particles, in this case, phonons. And these phonons, they behave as massless relativistic scalar fields in curved spacetimes. And then this could be observed by using, for example, 2-point correlation functions. So these 2-point correlation functions are a good experimental observable that I will use also in my project, my current project. So here in this plot, we see that there is the 2-point correlation function for before the RAM, so before the dynamical process in gray, and then after the dynamical process, we see that it has changed, and this is a good indicator for particle production. But what happens with fermions? So the aim of this project is to study fermions, and we suggest that maybe we can use moiré materials to do that because they are highly tunable as cold atom systems. And then, so we can manipulate the band structure and the interaction effects. And some of these moiré materials belong to the group of Dirac materials, which are characterized by these low energy fermionic excitations, which are described by the Dirac equation. So these low energy fermionic excitations, for some points, they follow this kind of linear dispersion relation, which is known as Dirac cone. So the most famous Dirac material is graphene, as you know. So let me go through this couple of slides really fast, because for sure you know these basic properties, and if not, Pablo already introduced some of them in his talk. So graphene is a honeycomb lattice, which has a unit cell with two atoms, which belong to two different sublattices, A and B. And then if we go to momentum space, we still have the honeycomb lattice. And if we focus on the first Brion zone, we see that in the edges, we have the 6 Dirac points, but only 2 of them are different. The other are related by symmetries. So in these Dirac points, the fermionic excitations, well, the electrons can be described, can be defined as massless relativistic particles. So yeah, they follow this linear dispersion relation. So we have Dirac cones. And one important feature is that the slope of the Dirac cones is defined by the Fermi velocity. But this is not a moiré system. So if we add another layer of graphene on top of it and we twist it, then we make it moiré. So now we have this twisted bilayer graphene. And if we focus in the low energy regime, in the flat bands, we still see Dirac cones. So they are protected by symmetries. And in the case of twisted bilayer graphene, these symmetries are time reversal and spatial inversion symmetry. So the Fermi velocity in this kind of systems depend a lot on the twist angle. And then the idea here is to introduce a time dependence to the system, for example, by, the Fermi velocity depends on the twist angle, and for some twist angles that are called magic angles, as Pablo explained, the Fermi velocity is nearly roughly 0, and it's very sensible to the change of the twist angle. So the idea is to introduce a time dependence in the system because we want to simulate an expanding universe. So we can do that, for example, by putting ultra-fast light pulses on the sample, or making a continuous rotation, or for example, applying pressure to the system. So twisted bilayer graphene, it's a good material for this kind of analog gravity simulations because it has a broad range of Fermi velocities. So just by changing a little bit the twist angle in the vicinity of the magic angle, the Fermi velocity changes really fast. Okay, but this is just an example, so I want to keep it general. I want to keep it for general moiré Dirac material. So let me introduce the most general Lagrangian for these materials. So here we have the Fermi velocity with which the fermionic excitations move. And then we also, what we do is to open a band gap in the Dirac cones. And this we also make it time dependent. So this band gap, it's not a scalar, it has a matrix form. And this is given by this gamma here. And this depends on the symmetry breaking of the system. So for example, if we put our twisted bilayer graphene sample into HBN, then this matrix will be proportional to the identity matrix. Okay, so if we take the variation of the Dirac adjoint of the action, then we get, of course, the well-known Dirac equation. And the aim of this project is to solve this Dirac equation for different band gaps and for different time dependencies. So all that is for condensed matter, but I said that I want to make a connection with cosmology. So let's see which is this connection. So first of all, I take again the Dirac-Lagrangian density for the Dirac material, and I compare it to the most general Dirac-Lagrangian that you can find in textbooks about quantum field theory in coarse spacetimes. And then just by comparing them, what we can obtain is the Fermi fields. So the Fermi fields are given by that, and they are related to the metric of the system by the Minkowski metric. So with that, we can write the line element of the system. And this line element of the system, we can compare it to the line element of an expanding universe. So this is the line element corresponding to Friedmann-Lemaitre-Robertson-Walker universe. And here A is the scale factor that governs the expansion of the universe. So by comparing the two line elements, what we see is that the scale factor must be inversely proportional to the Fermi velocity. So this is really interesting because with that, what we can what we can do is if we have an increasing Fermi velocity, this corresponds to a contracting universe. And if we have a decreasing Fermi velocity, we have an expanding universe. So yeah. But here in this Dirac Lagrangian, I didn't put the mass term. So what happens with this band gap that I opened before in the Dirac code? So first, let me introduce the conformal time that will make our life easier. So with this conformal time, we can write the Dirac equation, massive Dirac equation in this way, the one I showed you before. And then we can do the same for the cosmological case. So the Dirac equation for an expanding universe would be this one. So if you remember what I showed you in the previous slide, I said that the Fermi velocity has to be inversely proportional to the scale factor. So that leads to a direct relation between the cosmological fermionic mass and the band gap. So yeah. And this band gap, it's really important for particle production because it breaks conformal symmetry, and then it allows us to reproduce this particle production. It's essential. And also what is essential is to have a time-dependent ratio between the band gap and the Fermi velocity. It's not necessary that both of them are time-dependent, but at least one of them, and that their time dependencies don't cancel out. Okay. So now what we want to do is to solve the Dirac equation. And to do so, what we have to do is to choose a convenient expansion for the field. So here I chose this expansion, which corresponds to a spinless fermionic case in a honeycomb lattice. So we have two components of the field for the K point and two for the other Dirac point. And then we have two for one sublattice and two for the other sublattice. And since we are in flat space, what I can do is to expand this field in Fourier modes. So all the spatial content of the field is contained in this plane wave here. And yeah, we have also different ingredients. So C and D, they are fermionic and antifermionic annihilation and creation operators. And these operators describe a vacuum state. And U and B, they are called mode functions, and they contain all the time-dependent content of the field. So I can give you an example. So for example, in an static region, in a static space-time, you can expand these mode functions as Minkowski modes. Okay, so now we have our expansion, and what we can do is to solve the Dirac equation for different situations. So as I said before, the time dependence of the field is fully contained on the mode functions. So what we have to solve is the Dirac equation. If we expand it as I showed you in the previous slide, the Dirac equation leads to this kind of coupled system of differential equations. This will be for a mass term that is proportional to the identity. So it corresponds to the case where we put the sample of twisted bilayer graphene on top of an HBN substrate. Okay, so and now what we want to do is to solve these equations for each region of time. And I have one first stationary region, then we have a time-dependent region, and then something stationary again. And these stationary regions, I need them because only in the static regions is where we can define a vacuum state, is where the concept of quasi-particle makes sense. So we can define a vacuum state here with this set of operators, C and D, and then a different vacuum state in the third region, C tilde and D tilde, which define omega tilde at this vacuum state. These regions, so what we can do is to couple the Dirac equations, and then we see that they lead to this second order differential equation. And then you can clearly see that in region 1 and in region 2, the mode functions can be expanded in Minkowski modes, because if we don't have this time-dependent term of the band gap and the Fermi velocity, then this disappears, and then we only have the harmonic oscillator equation. And then what we are interested in is to relate the third region with the first region through Bogoliubov transformations, because the Bogoliubov coefficients are directly related to the observables of particle production. So to do that, what we will do is to study the Hamiltonian after the time dependence process has ceased. So the Hamiltonian here, it's not diagonal. So we start with a diagonal Hamiltonian for this set of operators. But now after the expansion, after the time dynamical process, we have this kind of Hamiltonian. And what we want to do is to diagonalize it. And to do so, we use Bogoliubov transformations. So with these operators, with this new set of operators, this Hamiltonian is diagonal. And one can obtain the Bogoliubov coefficients alpha and beta. And of course, the absolute value squares of alpha and beta is 1 because they should satisfy the Pauli exclusion principle. Okay, so this is all the theory, but now we can look at some observables that they can be related to experiments. So first of all, what we checked was the quasi-particle occupation number. So what we did to do that is to take the number operator of operators in region 3, so the tilde one, and we applied it into the initial vacuum state. And this led to the absolute value squared of the Bogoliubov coefficient beta. And this is always smaller than 1 because of the Pauli exclusion principle. And if this beta is different from 0, this is an indicator of particle production. So this will be the plot for this quasi-particle occupation number. But what happens if we don't start from a vacuum initial state and we start from a state that there are already excitations? So for example, we can start with a thermal state, and as you can see, a lot of things happen. So with a thermal state, what happens is that there is a Pauli blocking, because if you have fermions in some states, you cannot create more fermions in those states. So of course, there is a suppression of particles. And what we observe here, is that the higher the temperature, then the less particles are produced. Yeah. Okay. Another observable that we can check will be 2-point correlation functions. And here I chose this one because in the case of spinless fermions in honeycomb lattice, it's related to this staggered density contribution on the sublattices. So again, here one can observe the effect of Pauli blocking for different temperatures. And sorry, before I forgot to mention that this is for a dynamical region 1 that is 1 picosecond, and Fermi velocity that changes like that, and a gap, more or less like that. But we can adapt this depending on the Dirac materials that we are studying. So an interesting property of these 2-point correlation functions is that after the expansion has ceased, after the whole dynamical process has ceased and we are in region 3, we are static, they are still evolving in time. And this is curious. And this time evolution of the 2-point correlation function, these characteristic features of the 2-point correlation functions evolve with twice the speed of the Fermi velocity, the final Fermi velocity. Yeah. So with that, I would like to conclude my talk. So we have seen that Dirac materials can be a good quantum simulator for expanding universes, and then we also have checked that the band gap is essential for particle production, and also that we need a time-dependent ratio between the band gap and the Fermi velocity, but it's not necessary that both quantities are time-dependent. We only need one of them. And also we have seen different observables that give us signatures of particle production, like 2-point correlation functions or the number occupation operator. And then there's here my outlook. So there are a lot of things that we can investigate. So for example, one can introduce gauge fields. So we can introduce electromagnetic fields. And for example, reproduce the Schwinger effect, cosmological Schwinger effect, or one can study spatial curvature. That this would be also really interesting. Maybe it can be done by making a space-dependent Fermi velocity. And another thing that will be really interesting to study is if it will be possible with Dirac materials to reproduce this baryon-antibaryon asymmetry. And also, yeah, we are interested in knowing how the other bands of the band spectrum affect to the flat bands. And of course, the goal of analog gravity will be to have an experimental realization. So we would like to adapt this in order to have a real experiment. And yeah, with that, I would like to thank again my supervisors, Stefan Floschinger and Michael Scher, and I would like to thank you for your attention.